Alright, welcome back everybody. In this video we're going to look at using the trapezoidal rule to approximate the values of integrals. And basically when we use the trapezoidal rule, it's exactly what we did when we were using Riemann sums, except instead of putting rectangles under the curve, we're putting trapezoids under the curve. And there's a great deal of explanation earlier in the lesson as far as how we can best do this. So make sure you read through that. But basically, we've got two different approaches we're going to take. We've got one approach we're going to take when we have uniform width trapezoids, and one approach that we're going to take when we have non-uniform width trapezoids. Let's look at example 1. In example 1, the width of each of these trapezoids is uniform. There's a 1-hour time period from one time measurement to the next in this example. Excuse me. And so when I have a uniform trapezoidal width, I can just bring that trapezoidal width out in front. And then basically, when I'm building these trapezoids, I'm taking the average of these first two measurements, and the average of the next 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 two measurements. And so I'm taking all these averages of measurements, and you'll see what happens is that all the measurements in the middle get counted twice in their respective averages, whereas the measurements on the endpoints only get counted once. And so what I'm going to do is I'm just going to factor out that 1/2 from taking the average of all of these, and then I can just add all of the measurements together. I have the two that are counted only once, the 400 on the left, and the 0 on the right. And then all the other measurements are counted twice, so I'm going to double all of those. And this is the best approach for us to take when we have uniform width trapezoids. And so I've got 1/2 times 400 plus 2 times, and then I'll add up all the things inside this second set of brackets here. 780, 1140, 1440, 1640, 1700, 1750. So I've got 1/2 times 400 plus 3500. It's 1/2 times 3900. And so we're going to approximate that there are 1,950 gallons of oil spilled by the tanker. Alright, so that's a good approach when we have uniform width trapezoids. We figure out the width of each of the trapezoids. We pull the average out that we're using, and then we take the first and last measurements, count them only once, and then we take all the rest of the measurements and count them twice. Alright, so that's how we handle it if we have a uniform width trapezoid. What if we have non-uniform width trapezoids? Let's look at example 2. In example 2, we have the carbon dioxide emissions for Greenland at various points in time through the years. We're going to use the trapezoidal rule to approximate the total carbon dioxide emissions by Greenland in the period from 1965 to 2005. Now you'll notice the width of these trapezoids is not going to be uniform. We go from year 1965 to 1973. That's an 8-year span. And when we go from 1973 to 1986, it's a 13-year span. This is an 8-year span. This is a 7-year span. This is a 4-year span. And so what I need to do now, since I have non-uniform widths, is I'm going to need to calculate each trapezoid separately. So the first trapezoid has a width of 8, and then I'm going to take the average of the two bases, the two data values for those year points. and that's going to be the area of the trapezoid that represents the years 1965 to 1973. And then I'm going to do the same thing for the next trapezoid. And the same thing for the next trapezoid. And it looks like I'm going to run myself out of space here. Same thing for the next trapezoid. Looks like I wrote a little too big at the beginning here. And the same thing for the last trapezoid. Alright, and now all I need to do to find the approximation for the carbon dioxide emissions of Greenland is actually do these calculations. And so I've got 8 times 344 plus 557 over 2 plus 13 times 557 plus 319 over 2 plus 8 times 319 plus 502 over 2 plus 7 times 502 plus 539 over 2 plus 4 times 539 plus 557 over 2. Now before I hit enter, I'm going to make sure I typed all of this in correctly. Looks good. So we've got 18,417.5 thousand tons of carbon dioxide emitted by Greenland in that 40-year period, or 18,417,500 tons of CO2 emitted by Greenland in that 40-year period. By the way, if you think that's a lot, you should compare that to the amount of CO2 emitted by, say, the United States or China in that time period. I actually chose Greenland for this data set because it was a relatively small number compared to most other countries out there. I didn't want our answers to get too crazy big. Anyway. Alright, let's move on to the next page and example 3. One thing about the trapezoidal rule is when we put trapezoids under here, we can always determine whether it's an over-approximation or an under-approximation based on the concavity of the function that we're using in the approximation. And to keep this simple, I'm going to say, okay, here's a curve that's concave up. Well, if I put just one trapezoid underneath this, notice that the area of the trapezoid is greater than the area under the curve. And so when we're using the trapezoidal rule, if the graph is concave up, our trapezoids will over-approximate the area under the curve. If the graph is concave down, like this piece is here, then my trapezoid, there's my area of my trapezoid, will be bigger than the area, or pardon me, smaller than the area underneath the curve. And so in that case, the trapezoidal rule leads to an under-approximation. Alright. How do I use this? Well, let's look at example 3. We're going to use the trapezoidal rule with 5 trapezoids to approximate the area under the curve, y equals 3x squared plus 6 from x equals 1 to x equals 3. And we're going to determine whether this approximation is an overestimate or an underestimate. So I'm dividing it into 5 trapezoids. And we're going to make those trapezoids uniform width trapezoids. So each trapezoid is going to be 3 minus 1 over 5, or 2/5 units wide. And so, since I have uniform width trapezoids, I'm going to factor the width out in front, and I'll factor the average factor out in front. And then I need the value at the first trapezoid, its left endpoint, and the value at the last trapezoid's right endpoint, and I'm going to double the values at the other endpoints, which, since the widths are 2/5, I need the value at 1.4, 1.8, 2.2, and 2.6. Okay, so I've got 1/5 times f of 1, I substitute 1 into this function, that's just going to be 9. F of 3, I substitute 3 into that function, it's just going to be 33. Now these others are a little bit more difficult. Let's go ahead and we'll substitute 1.4 into the function. So we've got 3 times 1.4 squared plus 6. It's 11.88. And we'll do the same with 1.8. It's 15.72. And we'll do the same with 2.2. By the way, I've had several people over the years ask me, Mr. Thomas, how do you do that, where you get the whole entry back so that you can just change some values in it? And the answer to that question is by hitting second enter. It pulls back my previous entry, and I can just edit it and change that one value so that I don't have to retype all of it. Alright, and now I have all the values that I need for my trapezoidal calculation. And so I'm going to take 1/5 times 9 plus 33 plus 2 times 11.88 plus 15.72 plus 20.52 plus 26.28, and I get 38.16 for my trapezoidal rule approximation. Now, I want to know, is this an underestimate or an overestimate? In order to do that, I'm looking for the concavity of this function on that interval. So y prime here is equal to 6x. Y double prime is equal to 6, which means that this curve is concave up on the entire interval, since the second derivative is positive. And since it's concave up, that tells us that this is an over approximation, or an overestimate. Alright, and that's how I can use concavity to make a judgment. So I approximated the value of the area under the curve to be 38.16. It's an overestimate. Alright, that's the end of this video on the trapezoidal rule. See you guys next time. Have a great rest of your day.